everyone. So we have a great pleasure to introduce, most of you know Yuxuan, a CQIQC postdoctoral fellow, now for almost 2 years. Yeah, you have heard from Yuxuan a couple of times, I'm sure, from the quantum field visitors that he helped us bring here yesterday, for example, in Poland. So Yuxuan has been involved in many projects. That's really nice to see, with interacting, collaborating with, and really helping us collaborate also through his rich network with other people. So today we hear about, again, another project joined here, compressing quantum dynamics. Please, thank you.
All right. Thank you. Thank you, Davira, for the very nice introduction. And today I want to, share some of our recent results that we had in a series of projects that we did with, in partially with our guest speaker yesterday, Roland, and with my amazing advisors, Yang and Juan Calasquilla, and a bunch of other people. This is about compressing quantum dynamics using techniques in quantum machine learning. For those of you who are not very familiar with my research, I work on the intersection between these three different topics, namely quantum matter, quantum computation, and machine learning. Now there are different questions you can ask in between each of them. For example, between quantum matter and quantum computation, one could say, how do we use a quantum computer to better study quantum matters, and how do we use our knowledge in quantum matter to design better quantum computers, such as error correction, right? And in between quantum computation, machine learning, which is the focus of this talk, we ask questions like, does quantum computer offer speedups in training a neural network, or can we use machine learning tools in designing better quantum circuits or quantum architectures? And yeah, the focus of the talk will be the second of this relationship. And yeah, so it's like a synergy between hardware, software, and theory. So a little bit of motivation why we need a quantum computer to begin with. One of my favorite quotes from Deutsch, David Deutsch is quantum computing is a qualitatively new way to harness the nature. And this idea actually, maybe you have seen this quote 1,000 times, but for the sake of completeness, I'll still put it there. That is, because fundamentally, as proposed by Richard Feynman as early as 1981, that nature isn't classical. And for those of you who work on classical simulations of 2D materials or frustrated spin systems, you must have this experience that even simulating hundreds of qubits with restricted symmetry on a classical digital computer is very demanding, and thus this is why we need a quantum computer, due to the exponential scaling of the Hilbert space, after all. And so how are we doing now on this pathway to demonstrating quantum supremacy or quantum advantage, if you're calling it in a more modest way? That is, do we have a quantum computer nowadays? Do the best quantum computer outperform the best supercomputers, such as the Frontier we have in the world? Right? Even in performing some specific tasks, we of course don't expect them to at the current stage outperform supercomputers in every task. But can we get some speed up in some specific task? Now the thing is, even that it is a little bit hard. From a conversation with my former advisor, Scott Aronson, we according to him, we're still in the vacuum tube age of what you compare to a digital computer. That is where, if you look at the hardware design, it's more or less like, back in the 40s, 50s. We still haven't found something robust to noise, and it is very hard to perform useful computations at current stage. Even considering more advanced techniques. But soon, I think in the next 5 or 10 years, I think we're going to reach or go beyond this threshold. So we will have some useful, tasks that we can perform on quantum computer that outperforms the best, classical computer. And these tasks are not merely the task like, sampling quantum mechanics. There will be useful tasks like simulating dynamics as first posed by Richard Feynman. So this work, the inspiration of this work is heavily, based on this pursuit of quantum advantage or quantum supremacy. That is, how do we achieve the same operation with fewer gates, right? Like if we want to perform some computational task, just as in the classical computer, you have tons of ways of doing this on a quantum computer. On the right-hand side, I'm showing you an example of a quantum circuit. This is done with IBM Qiskit. Each little blocks here represent a gate. That is an elementary operation that you can physically perform on a quantum computer. And down here, I'm drawing you 2 circuits, C1 and C2. So it turns out that, just by directly looking at C1 and C2 and counting the number of lines and dots, as well as blocks on it, you can immediately find that C1 is more complicated than C2. Namely, performing C1 on a hardware device, it's harder to perform and less robust to noise than C2. But if you do the linear algebra correctly, like you do the matrix multiplication, you will find that C1 is actually equivalent to C2. So let's say we want to perform some task on a hardware. How do we, in the software level, reduce the number of resource costs? I think this is a very important question, especially we are at the current stage. Our devices are largely limited by errors and number of operations that one could perform. So this task turns out to be a very canonical problem known in the computer science community. It's a compiler design or compilation problem. So here, in this work, we mostly focus on compiling quantum dynamical simulations. That is, some dynamics, some unitary operation, and we want to do this in a variational way. We want to use a parameterized circuit to mimic this U generated by some either Hermitian or non-Hermitian Hamiltonian. I'll focus on the Hermitian for the first part of the talk. So for now, think of U as a large unitary generated by, for example, a Ising model, right? And then how do we use a parameterized circuit to approximate this dynamical operator with as few gates, but maximizing the accuracy of this approximation? Now, the canonical way of operating this very large unitary, just because we cannot do n-qubits interaction in the real hardware, you have to break it down into trotterization. Namely, you have to slice your Hamiltonian into non-commuting parts and implement the gates with minimized time slices. But that has been shown to be non-optimal, heavily non-optimal. So the reason why we propose this variational task is the variational circuit serves as a search in the vast Hilbert space, just like the example we showed previously, that although you may know some decomposition of your high-level operation that you want to implement, it might not be the optimized one. So the variational circuit here serves as a search, or like a search engine to find the shortest path on on these finding the geodesic in this vast Hilbert space, if you want, between the points, right? And this is done as early as people from 2018, which is people show this, that you can variationally save gates by doing this, then trautherization, but their scale were limited only to roughly 10 qubits. These early works back in 6 or 7 years ago. So the main challenge here is that how do we evaluate the difference between our target function U and target unitary U and this possibly highly complicated variational circuit V. Now, just to naively write down U can take you exponential number of memory classically, right? So I'm talking about doing this optimization on a classical computer, right? So the idea is we first run this optimization and then we put it on a classical computer, and then the dynamical circuit can be then put on a quantum computer, and one could execute this, repeating the same pattern again and again to reach like a longer dynamics, right? So you do it for like a truncated time slice. You compile for a truncated time slice, and then you repeatedly implement this on a quantum computer. But even then, writing down U and V and perform this trace distance calculation just naively is very demanding. You can either choose to write down U and V and perform this trace distance calculation, or you might be able to leverage the so-called Hilbert-Schmidt test. Namely, you double the system size using n numbers of ancillary qubits, and you do this Bell pair test between your prime and dual system. So yeah, if you execute the thing on the bottom, you actually get what is equivalent to the thing on the top. However, both of these are very computationally demanding. And then here comes the question, and then how does machine learning kicks in, and how does it help at all, right? So so the machine learning comes in. It seems like this is a very seems like we're just doing some variational optimization, and machine learning shouldn't be something that's relevant. But there's another way of viewing this task. That is, just imagine your target unitary is prepared by some secret experimentalist, and you, as a learner, that is a variational circuit, want to make queries to this experimentalist. And you want to query this experimentalist. By query, I mean you generate a state, an input state. You generate an input state and you feed into the experimentalist. You tell them to prepare this unitary for you, and they return you the date. They return with a state that is time evolved by this secret operation. So you can do so, and but then the question is, you as a learner, how many samples and what kind of data distribution, what kind of state ensemble you can pull these data from to efficiently learn your target unitary, right? So so usually in large language models, you hear about like these for example, Gemini or GPT, they takes like tons of data to train. But here quantumly, we're actually limited by the number of data that we can obtain, because for now we don't have like a large data set in terms of quantum. The quantum experiments we are running right now, they're still at dozens of qubits. at most maybe hundreds, but still very limited. So you don't have like, you know, TBs of training sample that you can use, right? And also, you know, we want these samples that we can draw from the ensemble to be prepared computationally efficiently. So formally, we can formalize this learning task by, you know, considering this empirical risk function. That is, you basically draw your states, your sample states from this ensemble, and D of Q, and you query V, you query U, and then you ask whether the state matches your prediction by your parameterized quantum circuit V. So in the limit where the number of samples, capital NS, goes to infinity, and when the ensemble is a hard random ensemble, then it's very apparent that this limit gives you the exact definition of trace distance. I mean, the trace distance, the physical meaning of trace distance between two unitaries is such that, you know, its average distance, one norm difference of its action on, you know, hard random states, n-qubit hard random states, right? But here are two problems. The first one is, you know, we were using a hard random ensemble here, and this violates our assumption too, that is your data should be easy to be obtained. Like just by a counting argument, you can see that, you know, with you know one minus exponential probability, you obtain a exponentially complex state if you draw states hard randomly from the unitary group as you 2 to the n, right? So that is not very optimal. We want something to be manageable, something to be, you know, generated by some low complexity circuit. So here it comes to the ideas of out of distribution generalization. So by this work by Carlos et al, they actually prove that you don't have to train your circuits on random hard random ensembles. Instead, the surprising fact they found is you could just train your circuits on random product states and still maintain a good fidelity of your training circuits when you test it on a different ensemble, namely the hard random ensemble. This seems highly non-obvious, and I'm not going to the proof details of this, but they found this equivalence because both of these circuit ensembles form what's so-called local scrambling ensembles. So in other words, we replace that. Here I'm replacing the, you know, there's only one thing changed here in the cost function. That is, I replace the original hard n ensemble with hard 1 tensor n ensemble. Okay, and now we solved problem 2. That is, the data can be generated efficiently because random product states you can just use single qubit K to generate, and classically that is also very easy to store, which is what we want eventually. But how many data do we need to use? Well, actually, it turns out is you know, not that bad. The number of data is you know, dependent on the number of variational parameters in your circuit. You know, capital T here refers to the number of variational parameters, and actually you can just see that if capital NS just scales with T times log T, it suffices to, you know, train with you know, suffices to give you a generalization risk that is constant in T and N. So, namely, for roughly a n parameter PQC, you only need capital NS roughly on the order of capital T for that number of samples for this training to maintain a good generalization accuracy. Yeah, any questions so far? So the generalization accuracy refers to you train it on some specific samples, but you want to generalize to the whole group, right? Like you want, yes. Right, hard random is it's a measure, right? It's a probability distribution measure. I mean, you don't do the integral, like you only do the integral when you calculate the expectation values. Sorry?
Can you substitute it for Clifford's?
For Clifford's, very good question. Clifford gates would form 3 design, and 3 design would also be locally scrambled ensemble. But Clifford gates are also, yeah, by this out of distribution generalization theorem, you could use Clifford, yes. But Clifford's also would take longer circuit depths to prepare. So you can just, yeah, get by with random products. Sorry? It's a
step vector scale, you can verify this. Doing an experiment.
yeah. So for experimental reasons, we choose to use product states. Also for numerical, yeah, purposes, because Clifford gates can be highly entangled. Yeah, so as you can see here, or we reduce our cost functions to a bunch of, instead of computing the trace distance between the very large unitaries, we now only need to sample its actions on some random product states, which permit a fast classical simulation, as well as a more robust experimental implementation. As you can see here on the bottom right, we try this learning and testing on some 1D T-film model. And you can see as we increase the number of samples, the training and the test, the risk would converge to each other. Like you see, if we only use 1 sample, there's a huge gap. But like this is on 80 qubits, some t equals to 0.5 evolution, and you can see they converge roughly already at 8 or 16 samples, right? So in practice, this performance is very good, which means we can learn shallow circuits at least in 1D efficiently, using this just to summarize. Because in 1D we can for constant depth circuits or quasi 1D, for example, that is a 2D stripe with 1 dimension fixed. We can use these TBD algorithms for fast simulation of these time evolved states, right? So this really permits a much better, a more scalable training result compared to previous works. So just to give everyone like a recap or like a overview of the algorithm. So first of all, we generate data. This is done through some TBD, and then we generate this prediction. Here psi i's are the same states sampled from random products ensemble, and V is some variational circuit. And we do gradient descents with standard packages like Torch on this step 3 to minimize this cost function. I mean, there's some technical details that we had to implement, such as a warm start to mitigate this, so-called barren plateaus in this variational training. But yeah, I haven't, put in every technical detail here. But after some math, some coding, this is what you get for the result. So compared with trautorization of older, so we have this Ising model with T-film with some longitudinal field plus some self-do, interactions. that involve some next nearest neighbor coupling, just to show the generic application of this algorithm. You know, and we compare the performance of the compiled circuit, you know, with some orders of trauterization on the same time slice. And we found that here, you know, for these parameter regimes, you get a couple orders of magnitude boost. Namely, you can reach roughly the similar accuracy in the C0 count. Now C0 is you know, 2 cubic gate count. That's what people usually care about in running experiments. Yeah, we can save roughly an order of magnitude gates, you know, in some of these dynamical events compared to trauterization. Different P's are different orders of trauterizations. Namely, the error is supposed to go with, you know, delta T to the P+1 on these trotters. Yeah, so this really shows the versatile of the methods applied in, you know, different kinds of 1D systems, and you know, and we can also test this long time limit generation, because you know, I promise you that we can train on small time slices, and you know, for long time dynamics, we could not train these circuits, but we could repeatedly apply these circuits to generate a longer dynamics. And here's the result. The 40-side Heisenberg model with disorders on it. Many of you are familiar with this. You know, with disorders, you of course get this confinement. Without the disorders, you can see the correlator just spread out like ballistically. Yeah, and we compare the TBD with like a very precise TBD with a much finer trauterization with this very crude variational circuit. I mean, not very crude, but like very fine infidelity, but requiring much fewer gates to implement variational circuits that we found using these machine learning tools. And it looks like these physical quantities would match pretty well. So, you know, yes. Like to train or to run the circuits.
So you need to do both training and actual calculation.
Yeah. So the idea is we do the expensive part on a classical computer, which is the training, and then for once we train the circuit, we give it to a quantum computer. So of course, if you take into account of training, then the classical cost would be much higher for the, you know, for the variational circuits, right? But yeah, so thanks to Roland, he discovered some amazing new technique. The training cost now is like the classical computational cost is reduced by some orders of magnitude compared to these results that we posted just I think 9 months ago or so, right? Yeah. So yeah, it's a lot of ongoing work, and you know, people usually criticize, or because we get one referee criticizing us for just doing, you know, 1D and quasi 1D. No, very impressive. So here's some 2D results. And you know, for 2D dynamics, this is really, you know, what experimentalists or like, you know, even theorists or rather like, you know, physicists in general would care more in general, because 2D systems permit, you know, more interesting physics, like, you know, quantum spin liquids, like, you know, yeah, frustrated spin systems, right? And yeah, in general, 2D is also very hard to 2D dynamics in long time is very hard to do because it doesn't have a nice, you know, MPS structure, and PAPS could, you know, time evolution with PAPS could also take a long time to compute. This also poses a question that whether we can compress a 2D circuit at all should we, stay in this, Schrodinger's picture? So we address this problem by considering a dual, sort of like a dual representation in the Heisenberg picture. Leveraging these new tools called, polypropagations, that really enables us to compute very large systems for these 2D and above systems. So the idea is, instead of like matching the predictions on each states of these unitaries, we think of it, the time evolution, as time evolving poly observables. So PJs here are some poly observables. And we want to match the actions of U and V on these poly observables. Now, some of you are not familiar with the, this double cat representation, but really, like I outlined here, this double cat operation between A and B inserted with some U is really just computing the trace of A U, B U dagger over 2 to the n, some normalization factor. So the whole idea of polypropagation is actually very simple. That if you, for example, either A or B commute with this U, then you can just propagate it through, right? Like you can swap A and U without any penalty, right? And then evaluating this trace would be trivial, because U dagger would just be identity, and here you have two very sparse polystrings, and you just have to match them each other. So you just have to check like one position whether they match with each other, right? Because they are like local poly observables, which is very important. However, let me not. However, in general, this is not true. Like when you propagate it through, you get some non-convenient terms still, so you have to make up for it. But many of these non-convenient terms turns out to have like very high poly weights, right? Considering you're permuting this observable P here through this circuit, the more layers you commute, there's a higher chance you get like more polystrings, but these polystrings can get really high weights. But you're trying to match two polystrings in the end. One of them is very high weight, and the other one is like very low weight. There's no way they could match with each other. So one could perform sort of truncations based on these like generated permuted polystrings, and cut off to sort of mitigate the number of branches that you get from this propagation, right? So in general, you get exponential poly passes, but the reason why people could perform like 2D noisy circuit simulation, for example, is because many of these passes are not important. So a lot of technical details exist in shaving off these unnecessary like poly passes in this propagation process. Okay. Now, skipping all of the technical details, here's what we considered in this soon-to-be published paper with the same collaborators plus Mathieu, who's now a first-year PhD at Juan's group at ETH. He did this amazing numerical calculation with PP on 3 different kinds of geometries. This open boundary grid, this this closed cylinder, or rather a torus, and this hexagon, this so-called heavy hexagon geometry that I think IBM is using for their hardware design, just to show the versatile of this method in general. So comparing the blue lines to the orange lines, we can observe on this 2D Ising model defined on these 3 different geometries, roughly in order of magnitude increase in the accuracy when you compare with the same resource. Namely, I mean, this might seem to be not as impressive as the 1D cases, but wait until you see the time-dependent Hamiltonians, right? So the thing about trotterization, in time-dependent Hamiltonian is, now you have to deal with when you truncate into slices. Now you have to deal with, the adjacent terms being non-commuting. So yeah, because the Hamiltonian now here I have a next nearest neighbor T film with this some Floquet drive, let's say. It's like a cosine wave drive on the on-site terms. So your trotterization become less accurate when you consider like these time slices are not even commuting with each other, which is actually very time dependent Hamiltonians. They appear very frequently in experimental physics as well as quantum control. And here we see that our performance is a couple order of magnitude better. The variational circuit's performance is a couple of orders of magnitude better than the trotterization. So there's a huge gap for huge I think there's a huge gap between these preset methods such as trotterization compared to our variational tools. And maybe it's a little bit hard to tell, but I think it's quite impressive that we were able to get it to work on a very large scale. That 2D lattices, we could extend this to 900 qubits, for example, which is far beyond any quantum computers we have on the market. So on the other hand, I also had this work with Youngback on these like non-Hermitian dynamics that I think previously in my last CQIQC talk I mostly focused on this one, so I'm just gonna flash you the results. So simulating non-Hermitian dynamics with these like quantum computers, there's a huge problem there. That is the non-Hermicity, of course. And how do you implement non-Hermicity on a quantum computer? So in this work, we specifically considered this one type of Hamiltonian that looks like a XXZ model plus like it has some non-Hermitian term on it, right? And the correlators one could consider, for this system is a connected density correlator. Of course, the non-Hermitian dynamics give you some, like your norm would grow or decay exponentially with your Hamiltonian. So you have to normalize your factor with this NT, a normalization factor. Yeah, but interesting about this non-Hermitian dynamics pose here is that if you do a quench, that is you start with JZ equals to 0 and prepare the ground state of that, and suddenly turn on the quench, then you actually get something abnormal. So notice here the Hamiltonian is all local. It's all like nearest neighbor. So usually the information could not go past Lie-Robson bound. Namely, like they should not exceed because like sitting in like a bunch of people standing in line, you're only talking to your neighbors. The information should not spread faster than order of 1 per unit time, right? But here you actually see something quite interesting. That is, through this TBD calculation, we can see that information do go past this so-called Lie-Robson bound. That is, you have like multiple light cones here. So Youngback and I were like, this is super cool. Why don't we toss it on a quantum computer? And turns out this is very hard. It's very hard because, like I said, it's due to this non-Hermicity. So just imagine you're trying to do a good old trotterization. you have to do this so-called block encoding because each little block here, it's a non-Hermitian object, right? So to implement a non-Hermitian product, you have to use ancillary qubits, but that is not even enough. Using an ancillary qubit and tracing out the qubit only give you CPTP mapping. But here it's non-Hermitian, it doesn't even preserve the norm. So what you do is you post-select on the measurement outcome of your ancillary qubit being some event. For example, 0 without loss of generality. Yeah, so you have to do this for all of your blocks in your dynamics, and for a 20 qubit chain, you can imagine this is very gross, right? Because each time you post-select, you only get like, in an experiment, you only get, say, a constant fraction of your measurement outcome to be in the desired state, say 0. So with this many gates, we estimate to do the thing that we actually did on the quantum computer, you would need 10 to the 19 sampling overhead, which is I don't know whether you can do that before the universe thermalizes, right? Yeah, so yeah, we did variational compilation on a fixed state for these. Of course, you cannot cast your non-Hermitian dynamics as a, you cannot cast it as a unitary object because it's non-CPTP. But you can cast it as its action on an initial state as a unitary, because it's merely a mapping between two states, two legal Hermitian states, in the Hilbert space. So I think this is also the idea of for example, imaginary time illusion, right? Or all of these. Yeah, you have to normalize to get a legal state, but then the action becomes, sort of unitary because it's a mapping between two states. So we did this compilation on this specific quench initial states, and specifically skipping all the technical details, we observed 2 peaks here. So on the left-hand side, we had an emulation of the actual experiment. This is what we would have got if we had 10 times of more quantum resources we had, yeah, we use these like tripions for experiments, and it's very hard to get the resources. So we really just got 2 time slices done out of this block. So we're looking at t equals 1, which corresponds to like roughly here, and t equals 2 roughly correspond to this slice. But I think the amazing thing is even like the signal level is like sub 1%. We're able to observe 2 peaks, indicating 2 Lieb-Robson bounds. So information being spread not in a single light cone, but in multiple light cones, thanks to these variational compilation methods. And this is yeah, some technical details. Yeah, this is some first known experimental demonstration on these non-Hermitian, I think non-Hermitian systems on that scale. So previously people did post-selection and they could only get like 5 qubits done. Okay, so putting everything together, just for the unitary case, by casting unitary compilation as a learning problem, we come up with a efficient BQC, namely variational quantum compilation method, drastically saving the number of quantum gates while preserve the fidelity of the gate, the overall operation, as well as long-term dynamics, both in 1D and 2D. And in 2D, this is thanks to these recently developed polypropagation methods. And for non-Hermitian systems, variational methods helps mitigates the post-selection issue. Without this, otherwise we would not have been able to perform any experiments per or crude estimation. And we observe these like supersonic modes on QC. Yeah, that's impossible with the traumatization. So, you know, a bunch of open questions, potential ideas, you know, put a couple there, you know, maybe you can do transfer learnings across families of Hamiltonians. This is because like you don't want, say you have some Ising type interaction, you don't want to, you know, for each J, each H, you just do the compilation again and again. So maybe you do it for a couple designated, you know, interaction strings, and then you use machine learning techniques such as transfer learning to generate the circuit that you need to prepare for, you know, other Hamiltonian parameters, right? And you know, this could also be used as some initialization scheme. Yeah, of course, I guess the more practical oriented direction could be, you know, one could consider this hardware oriented compilation. That is, what if you restrict your, you know, your circuit, or rather your gate stat, to some, you know, hardware limited connectivities and interactions. You know, more on the more theoretical side, you can ask, you know, what are the properties of these Hamiltonians that permit you know, fast forwarding. You know, this links to the dynamical Lie algebra stuff Roland talked about. But you know, maybe on the more practical side, you know, even the non-integrable models, which are supposed to be ergodic, supposed to, you know, in long time limit generate, you know, a quantum chaos. We still see that, you know, in practice you can get some sort of saving in the gate count. So what are the properties that permit these saving by variational circuit? Yeah, with that, I want to thank my amazing collaborators, as well as mentors, you know, here at CQIQC, at Vector, and, you know, at ETH Zurich, and at Los Alamos National Lab. I want to thank my friends for you know, the very nice discussions we had with I think many of you here. Yeah, and thanks for your attention.
Thank you very much. Do you have any questions?
If you go back to the place where you use, it helps, you know, post select, like easy post select.
Sorry?
How exactly does this help you post selection?
We use a unitary circuit, so the unitary circuit doesn't need post-selection. So even though a non-Hermitian dynamics is non-unital, its action on a quantum state is a unitary. So that permits a, yeah, variational compilation.
That means that all this, like breaking of the province and stuff can only happen on the scale like as big as your compiled fault.
Yeah, but if you leverage, you know, yeah, like what? Yeah, what do you mean?
Like both, like your system was like 100.
Oh, the experiment we did was only 18 qubits.
But suppose you have like a wireless experiment, then you would have to compile like solution smaller.
Yeah, that's one way of doing it. But you can also, I think one thing about this transfer learning method is you train on different scales, and then you find a map across different scales. So you don't have to do the expensive compilation on larger circuits.
If you both in this survey that if rolls and holds it.
Yeah, yeah.
And then you can possibly see like these like non-volatile
Sure. Yeah. Thanks.
So you've mentioned that for two-dimensional fluid you can do 30 by 30. So I'm curious about one dimension. Maybe also do 900 or is it that?
One dimension you can do whatever. You can do somebody recently showed that you can do thermodynamic limit. Yeah, to be fair, beyond the light cone, right? So you can just use the same parameter. So it wouldn't matter at that point. You see what I mean? Because you're compressing a constant time piece. So there's only so much correlator you can generate. So it doesn't matter, like, if you go beyond, say, for t equals 1, you go beyond like 40 qubits, everything is just the same. So 1D is not really that interesting. That's why we chose to go to 2D.
Follow up is like, is there any natural generalization to 3D, 4D, 5D?
Yeah, you can do that. Yeah. You can do it on any interaction graph. For these for these polypropagations. For 2D, you can also do the so-called belief propagation, which is a technique in the Schrodinger picture. So so whether we get advantage from PP, it really depends on what kind of Hamiltonian you're talking about. So for something near Clifford, PP is more robust. For something that's lower entanglement, then you can do like PAPS plus these like BP methods, which Roland is currently working on.
Can you clarify what is the physics under the traditional cones? What allows you to do? What is the physics under the traditional cones that you see? You have
So the derivation of this really let's go back to the model. Here you have a interacting fermion, but you can use it's an interacting fermion, but you can use techniques called you can do a bosonization, like use Latimer liquid, which is free boson field. Like you can map this to a free bosonic field and do the calculation there.
So the main cone comes from the non-unitary part? Is that?
No, the main cone comes from the unitary part, but like you would see multiple modes. Once you compute the two-point correlation in the field theory, you will see not one mode but multiple modes. So the effective Hamiltonian, if you were to map this to a Hermitian one, I think it has to be some long range Hamiltonian, like the unitary that after our compilation has to be some long range Hamiltonian.
Is there like a resource advantage using battery shield pump compared to the other
Like if you look at here, right? So just looking at the 2D Iding, for example, and this is not a very fancy model, but this same model is being simulated on this Quantinuum H2 device consisting of 56 qubits. And this is a paper published in March. They use trautherization roughly like here. You can see we still save roughly like, I don't know, like 30–40% gates compared to theirs. So there's a resource advantage if you do that. Now, if you do time-dependent evolution, that's another story. Like at the same accuracy level, like you can save, multiple,
Okay. Thank you very much.
Yeah, thank you.
Yeah.